Far beyond the familiar, a world shrouded in orange haze beckons. A moon, larger than Mercury, orbiting the ringed giant Saturn. Titan. For decades, it was a frozen enigma, a distant dot. But now, the whispers grow louder. NASA, the pinnacle of space exploration, poses a startling question: could life exist here? Not as we know it, perhaps, but something profound. A concept that challenges everything we understand about biology. The implications? Vast. Unsettling. Imagine an atmosphere, thick and hazy, where the sky itself rains not water, but hydrocarbons. Titan's atmosphere, unique in our solar system among moons, is almost as dense as Earth's, yet profoundly different. A towering blanket, roughly 1.5 times the surface pressure of Earth. Primarily nitrogen, yes, but laced with a crucial difference: methane. A key ingredient for an alternative chemistry, a parallel evolution. What forms might emerge under such an alien sky? And beneath that orange veil, liquids flow. Not the life-giving water we crave, but something far stranger: vast lakes and rivers of liquid methane and ethane. Imagine a boat navigating these alien waters, reflecting a sky forever obscured. Kraken Mare, Punga Mare, Ligeia Mare, names whispered by Cassini's instruments. These aren't temporary puddles, they are stable, persistent bodies, mirroring Earth's hydrological cycle, yet composed of entirely different elements. A truly alien hydrology. But then, the cold. A chilling, almost unimaginable cold. The average surface temperature on Titan plunges to a staggering -179 degrees Celsius, or -290 degrees Fahrenheit. Water, the universal solvent of Earth life, is frozen solid, harder than rock. This is where the conventional understanding of biology falters. How could intricate chemical reactions, the very dance of life, possibly occur in such an extreme, frozen environment? Or does life simply adapt, find a new rhythm? Yet, beneath that frigid crust, a tantalizing possibility emerges. Geophysical data, meticulously gathered by Cassini, hints at a vast subsurface ocean. Not of methane, but of liquid water. A global ocean, perhaps 100 kilometers beneath Titan's icy shell, likely salty, warmed by tidal forces from Saturn. Shielded from the harsh surface, this subterranean realm offers a profound sanctuary. A protected crucible, where water, the very essence of Earth life, could persist. Life, anywhere, requires energy. On Earth, sunlight drives photosynthesis, chemical reactions power deep-sea vents. What could fuel life on Titan? Within that subsurface ocean, hydrothermal vents, akin to those found in Earth's abyssal plains, could provide chemical gradients. On the surface, solar energy, though diminished, still reaches. And a phenomenon known as cryovolcanism, icy volcanoes erupting water and ammonia, hints at internal heat. Energy sources exist. Different, yes, but potent. Titan is a factory of complex organic chemistry. Its atmosphere is a giant chemical reactor, churning out intricate hydrocarbon molecules, called tholins, which rain down to coat the surface. These are the very building blocks, the fundamental Lego bricks of life. Experiments have shown that under Titan-like conditions, these molecules can self-assemble. Not life itself, perhaps, but the precursors, the raw materials. The stage, it seems, is meticulously set. But for what exactly? Our understanding of Titan was revolutionized by the Cassini-Huygens mission. Launched in 1997, arriving in 2004, Cassini orbited Saturn for over 13 years. Its Huygens probe, in 2005, became the first spacecraft to land on a moon in the outer solar system, parachuting through Titan's atmosphere and touching down on its icy surface. The images, the data, an unparalleled treasure trove. Every bite deepened the mystery, confirming a world of astonishing complexity. And now, NASA prepares for its next audacious leap, Dragonfly. A rotorcraft lander scheduled to launch in 2027 and arrive in 2034. It will hop from one location to another, exploring Titan's diverse environments, sand dunes, impact craters, the shores of methane lakes. This isn't just a flyby, it's an expedition. Dragonfly will directly sample materials, analyze chemistry, and search for biosignatures. It will be our boots on the ground, or rather, our rotors in the air. Some scientists draw striking parallels between Titan and early Earth. Billions of years ago, Earth's atmosphere was also nitrogen-rich, with abundant methane. Before oxygen, before complex life, our own planet was a crucible of organic chemistry. Titan, in a way, might be a frozen time capsule, preserving processes that predated terrestrial biology. A planetary experiment, played out on a different canvas. Could it be a glimpse into our own deep past, or a fork in the evolutionary road? But what exactly are we searching for? Our definition of life is inherently Earth-centric, carbon-based, water-dependent. On Titan, with its hydrocarbon seas and cryogenic temperatures, life would almost certainly be radically different. A silicon-based life? Methane-based biochemistry? It forces us to expand our very definition of what life means. To peer beyond the familiar, into realms of theoretical biology, where the rules might be entirely rewritten. Consider the very air Titan breathes. A thick, opaque shroud. Its surface pressure isn't the vacuum of Mars, nor the comfortable embrace of Earth. It's a heavy blanket, a persistent pressure that could shape any emerging biology in ways we barely comprehend. This isn't just an environmental detail, it's a fundamental parameter. A planet's atmosphere dictates so much: weather, liquid stability, the very physics of how things move and interact. The very nature of liquid on Titan forces a profound comparison. On Earth, water is the universal solvent, facilitating countless biochemical reactions. On Titan, its surface liquids are hydrocarbons. This isn't a minor distinction, it's a paradigm shift. Imagine cellular structures, metabolisms, reproductive strategies, all built upon a different liquid medium. The chemical kinetics, the molecular interactions, they would operate under an entirely alien rulebook. What implications does this hold for life as we ponder it? What does life truly need? A solvent, a source of energy, and complex organic molecules. Titan possesses all three, albeit in forms radically different from our own. Liquid methane and ethane as solvents. Tidal heating, cryovolcanism, and attenuated sunlight as energy sources. An atmosphere and surface rich in tholins and other complex hydrocarbons as building blocks. The raw components are undeniably there. But assembly, organization, evolution, that's the true mystery. For any life resembling Earth's, Titan presents insurmountable obstacles. The intense cold alone would render most terrestrial biological processes impossible, freezing proteins, stopping enzymatic reactions dead. The absence of surface liquid water. The lack of free oxygen. These are not minor inconveniences, they are fundamental barriers to carbon-water-oxygen-based life. So, if life exists, it must be something entirely, astonishingly different. A different tree of life, with different roots. The presence of cryovolcanism is a game-changer. These ice volcanoes don't erupt molten rock, but rather liquid water, ammonia, and other volatiles from deep within Titan. This process could bring vital nutrients from the subsurface ocean to the surface, potentially creating localized warm zones or enriching surface environments. It also hints at an active interior, a dynamic world, not just a static ball of ice. A flicker of internal heat, a potential hotbed for exotic chemistry. Tholins. These complex organic compounds, formed by solar ultraviolet radiation interacting with atmospheric methane and nitrogen, are everywhere on Titan. They give the moon its distinctive orange hue, coat its dunes, and dissolve into its lakes. They are the planet's ubiquitous organic raw material. their sheer abundance suggests a readily available feedstock for any hypothetical biology. Could these versatile molecules, given enough time and the right conditions, spontaneously organize? It's worth a brief glance at another Saturnian moon, Enceladus. This smaller moon also harbors a subsurface ocean, but one that actively vents water vapor and organics directly into space from its south polar geysers. Enceladus presents a more direct path for sampling an ocean world. Titan, however, offers a thicker atmosphere, a more Earth-like complexity, and surface liquids. Two very different canvases, both painted with the tantalizing brushstrokes of potential biology. So, what might this life look like? It's a question that stretches the imagination to its breaking point. Perhaps microbes that metabolize ethane, generating hydrogen as a waste product. Or complex, slow-moving organisms, adapted to the intense cold, using ice as a structural component. Could they be transparent, or glow with bioluminescence in the eternal twilight? The forms are limitless, constrained only by the extreme chemistry of their environment. A truly alien biology. The Dragonfly mission is not just searching for simple signs of life. It's searching for answers to fundamental questions about habitability itself. Is life a unique Earth phenomenon, or a cosmic inevitability? If Dragonfly finds evidence, perhaps unusual chemical signatures, unexpected energy gradients, or even structures that defy geological explanation, it would rewrite textbooks. The wait is long, but the promise, immense. The hunt for life beyond Earth. Truly, it begins on Titan. Should NASA confirm even the most rudimentary, non-water-based life on Titan, the implications would be nothing short of revolutionary. It would shatter our Earth-centric biases, demonstrating that life is far more versatile, far more diverse than we ever conceived. It would push the boundaries of astrobiology and chemistry, forcing us to rethink the very definition of a habitable world. And it would fundamentally alter humanity's place in the cosmos, knowing we are not alone.